To answer the first question, why RNA cannot make double-stranded helix like in DNA. So we have to look at the difference between RNA and DNA. The only one position that RNA is different from the DNA is this carbon. DNA has no OH, but RNA you have like OH over here. And just that OH you cannot forming the double-stranded helix. That means the OH group up here ruins everything, right? Ruins everything. You may notice that in RNA system, you can have this hydrogen bond system structure as well. In RNA, in tRNA and messenger RNA, you can have this kind of thing, right? Because for tRNA, you have tricodon. For mRNA, you have tricodon, and after the tricodon is matched, then you can make polymerization of the amino acid up here by the ribosomal RNA, right? So that means somehow that hydrogen bonding still happens, but it is not permanent. It's non-permanent. Between tRNA and messenger RNA is non-permanent in the translation process, right? And in transcription process as well, if you have the DNA and then you like making messenger RNA out of DNA by transcription process. No? So in making up RNA from the DNA, you have to use this hydrogen bonding to like copy the gene from DNA on top of your messenger RNA, thing like that. So you can have this kind of hydrogen bonding as well, but it's not permanent. Because after you constructing messenger RNA, the messenger RNA just leaves your DNA system and go out of your nucleus, synthesis the protein afterward on the ribosomal RNA and everything. So that means the design is like hydrogen bonding system of the base pairing, or I would say the base pairing system in RNA is not as permanent, is not as strong as DNA. So after evolution, as you may know, the very simple living organisms like RNA, like virus, you have only RNA. But with evolution, we're constructing DNA in order to preserve the genetic, right? To make it stronger and make it more difficult to be mutated by some other factors in environment. That means the living organisms just decided to cut this OH out, and then the hydrogen bond getting stronger, and you have double-stranded helix very strong. So why? The OH character of the OH or the alcoholic functionalities in your organic compound. You know that OH can make hydrogen bonding, right? So that hydrogen bonding from this OH may ruin all the hydrogen bond system over here. Right? So some may think that the OH may hydrogen bonding with this base pair or the next base pair. But the very important mechanism over here is if you have OH here, very polar functionalities, the hydrogen bond is not only this OH with the base and ruins the base pairing system, but this OH will also hydrogen bonding with the water molecule. Right? So let's bring water molecules around. So with water molecules around here, right? With the water molecule around here, the water molecules can perturbate all the hydrogen bonding system. And then your hydrogen bonding system is not permanent because it's not only base pairing, but you have water, a lot of water down here. And these water molecules can then ruin the whole base pairing system, hydrogen bonding here, because it's competitively bound with the base around here. So instead base pairing together, you have water molecules to have competitive binding with hydrogen bonds. Okay? So this is why RNA has no permanent hydrogen bond system of the base pairing. Now, next question. I would erase the water molecule out first. Next question, I want you to show or want you to draw the base pairing between inosine and cytosine. Okay, it would be more difficult if I asked you which kind of base that the inosine can perfectly bound with. But now I just tell you the truth that I can bound with cytosine, the base. Now cytosine structure is over here. So what you have to do is put the inosine instead of guanine, right? You substitute the guanine unit with the inosine unit, and that's it. Okay, so this is not G anymore. This will be I. Okay, so the inosine, you have the carbonyl up here. You have NH, but you just cut out the NH2. So this is difference between inosine and guanine. Guanine, you have amino group, but for inosine, you don't have this amino group. You just cut this amino out. Deamination is the process. So after deamination, you have this inosine. And as you can see, inosine, then you have acceptor. I would label by green. Acceptor and donor. For cytosine, you have donor, you have acceptor, and you have acceptor over here. But the acceptor matched with nothing because you don't have anything pointing downwards, down here, right? That means you have only 2 hydrogen bond system between inosine and cytosine. And this can imply that the base pairing between inosine and cytosine is somehow weaker than the base pairing between guanine and cytosine as well. Because between guanine and cytosine, you can constructing 3 hydrogen bondings. But for inosine and cytosine, you can construct only 2 hydrogen bonding systems. So this is how the IC is a bit weaker than G and C. Okay, so the number of hydrogen bonding plays a very important role in the strength of the hydrogen bonding system. So that means if you're starting from DNA system, okay, if you're starting from DNA system, the DNA double-stranded, if you have a lot of G and C, that means the DNA double-stranded helix is very, very stable. But if you lack of G and C, if you have so much of T and A, then the number of hydrogen bonding in the whole system is less than the GC-rich DNA system. So GC-rich DNA system tends to have higher stability. And if you want to break it out by heating, it requires higher temperature as well. So as you can see, if we know if we understand the basic concept of hydrogen bonding, the basic concept of hybridization, so we can describe almost every properties, physical properties and chemical properties of DNA and RNA. Very easy actually. Okay, so that's all about the DNA system that I want you to know. And this is the end of the nucleic acid. Okay, now we're going to look at the next functionalities, the next biomolecules, proteins. Okay, so we'll see you again in the topic of proteins in the next flipped classroom.